Hello and welcome to the course An Introduction to MATLAB. So what is MATLAB? MATLAB is a non-free programming language used for analyzing data, develop algorithms and create models. MATLAB users come from various backgrounds such as engineering, science and economics. In this course, no previous programming experience is assumed, and that means that we're going to start from the absolute beginning. The code from this course is provided in a GitHub folder, and the link to that folder you can find in the video description. In general, it is encouraged to experiment with the code for good learning results. In this course, the first chapter that we're going to start with is called Getting Started. Then we continue with matrices and functions, saving and loading data, indexing, plotting, and then finally some statistics. So with that said, we are ready to start the course, so let's go.
If you have installed MATLAB or had it installed from before, it is nice to be able to see what version you have and what toolboxes you have installed. This is easily done by typing in the command ver in the command window. So I type in ver and press enter. At the time for this recording, we see that I had version R2020A. And if you have an older or newer version, it really doesn't matter. But if you have a really old version, such as 10 years old, then consider updating your version, which you do by reinstalling MATLAB. We also see that I have the third update for this version, and usually what they do in these updates is to fix some bugs. To check for updates, go to the Home tab, Help, and Check for Updates. Here I get the message that my MATLAB is up to date, so we don't have to do anything here. Here we see what toolboxes we have installed. For this course, I recommend the following 6 toolboxes. The only toolbox we really will need in this course is the first one, Statistics and Machine Learning. But if you continue to read mathematical statistics beyond the basic course, you will probably need the other ones as well. For instance, system identification is used in a course such as time series analysis. Installing toolboxes is straightforward. You go to Home tab, Add-ons, and Get Add-ons. Once in this window, you can search for the toolbox you want to install. So in my case, I want to install Statistics and Machine Learning Toolbox. So I have written Statistics and Machine Learning, and I search for that. And we see that I have that toolbox installed. So just to demonstrate the principle of how to install toolboxes, I will choose Sim Biology Toolbox. And once Sim Biology Toolbox is selected, you simply press Install and continue to follow the instructions. If you would like to uninstall some toolbox, that is also easy to do. You go to Add-ons, Manage Add-ons, and then depending on what toolbox you want to uninstall, you select that one here and press Uninstall. So, make sure that the Statistics and Machine Learning toolbox is installed and we are ready to go. Main features of the desktop layout in MATLAB is Current Folder, Command Window, and Workspace. In the current folder, we see what files are available in our current folder. In my case, the current folder is called MATLAB course. In the command window, we execute MATLAB code. In the workspace, the variables that we create will be displayed here. So, in the command window, we can do some basic calculations such as 1 plus 1, 10 multiplied by 10. And we can also use some basic math functions such as log of 100. If we want to calculate the base 10 logarithm of 100, we can write log 10 of 100. And we can, for instance, also calculate the value of sine of pi divided by 2, and then we expect to get the number 1, which is exactly what we got. In MATLAB, we can also handle complex numbers, and the way to do that is to write an I after the imaginary part. So for instance, writing 1 plus 2i will produce the complex number 1 plus 2i. If we use the function imag, which returns the imaginary part of a complex number, so I write imag 1 plus 2i, then we'll get the answer 2 because the imaginary part is 2. If you want help about something in MATLAB, the keyword to use is called help. So for instance, writing help log will display a short help text about the function log. If you want a more complete documentation about something in MATLAB, the keyword to use is called doc. So for instance, writing doc log will display a complete documentation of the function called log. So here we have the syntax, we have a description, and we have some examples. And in general, the documentation in MATLAB is really good, so it's a good habit to read the documentation and you will learn a lot from it. If you want a complete list of the elementary math functions, you can write help lfun. And then we see that some of the elementary math functions include trigonometric functions, exponential functions, complex functions, and so on. And if you want a list of more specialized math functions, you can write help specfun. And then we will get a list of more specialized math functions. For instance, we see that there are some number theoretic functions, such as greatest common divisor, and so on. In MATLAB, it's easy to create variables. So now I will create a variable called a, which is equal to 1. And then we see that a have popped up here in the workspace. I will create another variable called b, which will be equal to 2. And b has also popped up here in the workspace. Now, when I have the variables a and b, I can, for instance, write a plus b. And then I will get the answer 3. And one thing to notice in this case is that I did no assignment. I simply wrote a plus b. Then I get a new variable that's called ans, which stands for answer. And this new variable ans is also stored here in the workspace. So in general, if you do no assignment, you will get a new variable that's called ans, which stands for answer. It's also easy to create vectors in MATLAB, and the way to do that is to use square brackets. So if I create the vector x, then I write equal sign and I insert square brackets. So 1, 10, 100 and 1000. Now I have created a vector x, which consists of the elements 1, 10, 100 and 1000. If I now want to calculate the base 10 logarithm of each element, then I simply write log 10 of x, and I get the base 10 logarithm of each element. And the base 10 logarithm of 1 is 0, and base 10 logarithm of 10 is 1, and so on. It's also easy to create matrices in MATLAB, and the way to do that is to again use square brackets. So if I create a matrix called A, I write equal sign and insert square brackets. Then I can, for instance, write 1, 2. That's the first row. And to get to the next row, I write a semicolon. So here is a semicolon, and that means that we go to the next row. Then I want the next row to be equal to 3 and 4. Pressing enter returns the matrix A consisting of 1, 2, 3, and 4. And also the matrix A is displayed here in the workspace. If I now, for instance, write A bracket 2, 2, this will return the element from the second row and second column. So I expect to get a 4, which is exactly what I got. If we write sum A, then we will get the sums of each column. So here I have written sum A, and then we see that I got the sum of each column, in this case 4, and in the second column 6, which is those numbers. If I want to get the exponential of each element in matrix A, I simply write exp A, and then I get the exponential of each element in matrix A. One thing to notice now is that in the workspace we have our variables and we have some information. If you want to change the information provided, you can simply right-click somewhere here in the headers. So I right-click here, and then we can, for instance, choose to display the maximum as well. And now you see the maximum value there as well. Another way to create a matrix is to use a function called rand. And rand produces uniformly distributed random numbers between 0 and 1. So if I write rand 3, 2, this will produce a 3 by 2 matrix consisting of uniformly distributed random numbers between 0 and 1. And here I have it. And if you sometimes forget the arguments of a function, then you can simply write the function and one bracket, and then you will see what arguments you can put into it. If you want to reuse some code you have written in the command window, you don't need to write it again. So for instance, if I want to calculate exp of A, I could write exp A again, but I can also use the arrow keys in my keyboard. So I press the arrow key up, and then I can choose which command I want to rerun. If you write CLC, this will clear the command window, so now it's fresh. And if I, for instance, write clear A and big A, this will clear the variables A and A. So notice now how these variables will disappear. They have disappeared. And if I simply write clear, then all the variables in my workspace will disappear and are removed. So in this video, we wrote our code in the command window, but in practice, one writes the code in a script. And this is the topic of next video. In the previous video, we wrote our code directly in the command window. For instance, typing 1 + 1 returned the answer 2. In practice, you seldom write your code directly in the command window. What you instead do is that you write your code in a script. In that way, you get a much better overview and it gets a lot easier to write your MATLAB code. So to open up a new script, you go to the Home tab, and here you can press New Script. We also see that there is a keyboard shortcut, which is Ctrl-N. So if I press Ctrl-N, I have opened up a new script, and I could write my code here. But for this video, I have already prepared a script, so we can close this down and continue in this script that I have prepared. So once you have a script, it is good practice to divide your code into sections and to comment on your code. To divide your code into sections, you type 2 percentage signs, and then we get a new section here. And that it's a new section is indicated by this yellow background color. If you want to comment on your code, you type 1 percentage sign and then write whatever you wish. For instance, this is a comment. If you want to comment out certain lines of your code, there is a nice keyboard shortcut for that, which is Ctrl-R. So if I press Ctrl-R, 1 percentage sign is produced. If I press Ctrl-R again, another one is produced, and so on. If I want to remove the percentage signs, I simply press Ctrl-T. If we continue to the next section, which is called Section 1, Writing Code on a New Line, it's important to know that if you want to write code that spans over multiple lines, then you have to use the ... notation. For instance, 1 plus 2 plus ... means that I'm continuing my code on the next line. So if I press Ctrl Enter to run this section, so I press Ctrl Enter, then we see that the answer is 13, which you can easily verify that the sum of these terms is exactly 13. If we continue to the next section, section 2, terminate output, in this section I have created one variable a, which is equal to 1 plus 1, and another variable b, which is equal to 1 plus 2, and in the end I have typed in a semicolon. What a semicolon does is that it suppresses output, but the computation or assignment is still carried out. So if I clear the command window by writing CLC, and now I press Ctrl Enter, we see that a is equal to 2, but b has not been printed out in the command window. But the assignment of this variable has still been carried out, which we can see in the workspace. Here we have the variable b, just as we have the variable a. So the semicolon suppresses output, but still does the computation or assignment. And this semicolon we're going to use throughout in this course, and it is very handy if you, for instance, have lengthy calculations and don't want to show all the middle steps. So semicolon is an important command. In section 3, running your code, we will go through different ways of running your code. If you want to run your whole script, you can go to the editor and here press run. Then it will run the whole script, which is called chapter 1, getting started. The name of the script is here. So I press run and the whole script and all of its sections are run. If you want to do it another way, you can simply write the name of your script in the command window, so chapter 1. And now I don't have to type the whole name, I simply press tab and it gets autofilled. If I now press enter, we have run the whole script again. So to make this clear, I clear the command window and now I type the name of the script, press tab, and we see that we have run the whole script. If you want to run a specific section, you can press Ctrl Enter, or you can go to the editor and press Run Section or Run in Advance. If you press Run and Advance, you will run the section and jump to the next section. If you want to run specific lines of code, you can select that line and simply press F9. So I press F9, then I only run this line of code. Continuing to section 4, undocking script. If you're working on two screens, it's sometimes very handy to undock your script. This is easy to do. You press this arrow here and press undock chapter 1, getting started. And now we have two windows. This means that you can drag this window to the next screen. And as I said, that's very handy if you're working on two screens. But in this video, I'm working on one screen, so I can redock this chapter 1. And now it's back where it was. Finally, in section 5, I have done some recap from the previous video, and the purpose there is to demonstrate how a script in the real world could look like, and for you to recap that lecture. So have a look at it. In this video, we are going to create some vectors, and let's call our first vector x. To create a vector, you insert a square bracket and type in the elements that you want the vector to consist of. Let's say I want to have the elements 1, 2, 3, and 4. If I run this code, we see that we get a vector consisting of the 4 elements that I have typed in. If you want to have a column vector, you can write x prime, where prime is the transpose operator. And we see that we now got a column vector. If you want to create a column vector manually, you can do that. So let's call it y. Again, you insert a square bracket to create a vector. And this time, to start on a new row, you use semicolon. For instance, 3 semicolon 10 semicolon 7. This will create a column vector consisting of these three elements. So if I select this line and press F9 to run the code, we see that we got a column vector consisting of the three elements that we typed in. So the semicolon lets you begin on a new row. If you would like to create a unit-spaced vector from 1 to 14, this can easily be done by the colon operator. You simply write 1 colon 14, and then we see that we got a vector consisting of the 14 elements that are unit-spaced. In general, the syntax for the colon operator is the following: start, step, end. So for instance, typing 1 colon 3 colon 14 will create a vector with the first element equal to 1 and then the step size is equal to 3. So running this code, we see that the first element is 1, and then we do a jump of size 3 to 4, then a jump of size 3 to 7 again, and so on until 13. And the last element is 13 because that is the last step we can do before passing 14 with step size of 3. Another example of the colon operator, we can for instance type -10, 2, 3, and then this time the first element is -10 and the step size is 2. So running this code, we see that the first element is -10, and then we do a jump to -8, which is a step size of 2. A very related function to the colon operator is linspace. The syntax for linspace is the following: linspace x1, x2, and big N. This generates endpoints between the numbers x1 and x2, which are linearly spaced. If you put no argument for n, then by default it is 100. So for instance, typing linspace 1, 10, 3 will create 3 points between 1 and 10. So running this code, we see that we got 3 points. If I type linspace 1, 10, then since I put no argument for n, it is by default 100, so we will get 100 points between 1 and 10, which we see here basically. A related function to linspace is called logspace, so you can write doc logspace and read about it yourself. To create a matrix in MATLAB, you insert square brackets and then you type in the elements column-wise. To begin on a new row, you type a semicolon. So selecting this line and pressing F9 to run the code, we see that we have created a 2x3 matrix where the first row is 1, 5, and 7, and the second row is 2, 1, and 3. So as I said, to begin on a new row, you type a semicolon. This is sort of the manual way to create matrix, but there are also some functions that create matrices. For instance, zeros 3 will create a square 3x3 matrix consisting of zeros, while zeros 3, 2 will create a 3x2 matrix consisting of zeros. A very related function is called ones, and you can guess that this will create a 2x3 matrix consisting of ones, as you see here. A very related function to zeros and ones is called repmat, but it is a little bit more general. For instance, typing repmat 2, 3, and 4 will create a 3x4 matrix consisting of 2s. So with repmat, you can choose what you want the elements to be. Another example of repmat is this. So what we do here is the following. First, we create a matrix where the first row is 3 and 2, and the second row is 4 and 5. Once this matrix is created, we repeat it twice in the row dimension and 3 times in the column dimension. So running this code, we see that first we created a matrix where the first row is 3 and 2, and the second row is 4 and 5, and then we repeated this twice in the row dimension and 3 times in the column dimension. So experiment little with this and you will figure it out. Then we have a function that is called magic. If I, for instance, type magic 3, I get the following matrix. So to find out what it really does, we can write help magic, and then it says that the row, column, and diagonal sums are all equal. So let us check this. The first column sum is 15, the first row sum is also 15, and the diagonal sum is also 15. So magic is another way to generate a matrix. Some functions operate essentially on scalars, but operate entry-wise when applied to a vector or a matrix. For example, the base 10 logarithm of 10, we know that is equal to 1, and sine of 3 pi divided by 2, we know that is equal to minus 1. There is nothing strange in this example. But if we now create a vector y consisting of the elements 0, pi divided by 2, pi, and 3 pi divided by 2, we can ask ourselves what happens if I apply sine to the vector y. So if I run this code, sine of y, we see that we get the answer 0, 1, 0, and minus 1. The reason for this is that sine of 0 is 0, sine of pi divided by 2 is 1, and so on. So when applying a scalar function on a vector, we operate entry-wise. The same logic applies when we apply a scalar function to a matrix. So if I run this code here we have the matrix A consisting of the elements 1, 100, 10, and 1000. We know that the base 10 logarithm of 1 is equal to 0, the base 10 logarithm of 100 is equal to 2, and so on. So again, we applied a scalar function to a matrix, and then the function operates entry-wise. For reference, if you want to have a list of elementary and specialized math functions, you can type help elfun and help specfun. So check it out. Vector functions operate on a vector. When using a vector function on a matrix, we get a row vector containing the results of the function performed on each column. So for example, if I create matrix A and then type sum of A, then I will get a row vector containing the sum of each column of matrix A. Looking at matrix A, we see that the sum of the first column is equal to 12, and 12 is exactly what we got here, and the sum of the second column is equal to 4, and 4 is exactly what we got here, and the same goes for the third column. If I display matrix A again, and then type sum of A, 2, then we will get a column vector containing the sum of each row of matrix A. And looking at the first row of matrix A, we see that the sum is 18, and 18 is exactly what we got here, and the same goes for row 2 and row 3. If I type sum of A, apostrophe, all, apostrophe, then we will sum all the elements in matrix A, and you can verify for yourself that the sum of all elements in matrix A is exactly 29. In general, the syntax for the sum function is the following. In the first argument, you specify the matrix, and in the second argument, you specify the dimension. By default, the dimension is equal to 1, meaning that you get a row vector containing the sum of each column. If you specify the dimension to be equal to 2, then you will get a column vector containing the sum of each row. And finally, if you specify the dimension to be equal to all, then you will sum up all the elements in matrix A. The mean function and the median function works in exactly the same way as the sum function, so you can try that yourself. If you want to compute the variance in MATLAB, that is straightforward to do. The general syntax is the following. In the first argument, you specify the matrix. In the second argument, you specify the weighting scheme. By default, the weighting scheme is equal to 0, meaning that you normalize by number of observations minus 1. If you specify the weighting scheme to be equal to 1, then you normalize by number of observations. And the third argument, dimension, works in exactly the same way as it does in the sum function. So for example, running this line of code will give us a row vector containing the variance of each column in matrix A, where we normalize by number of observations minus 1. And here we have the result. If we run this line of code, we will get exactly the same thing, because by default the weighting scheme is equal to 0, and by default the dimension is equal to 1. Looking at these two lines of code, they are doing exactly the same thing. The only difference is that in the second argument here, we are using an empty square bracket. The empty square bracket means that you're using the default argument. So this is very handy to use if you, for instance, want to use the default argument but don't remember what it is. So the empty square bracket is very handy. If we run this line of code, we will compute the variance of all the elements in matrix A, and here the empty square bracket in the second argument means that we're using the default argument. And you can recall that the default argument for the weighting scheme is equal to 0. Finally, if you want to compute the standard deviation, then you can use the function std, and it works in exactly the same way as the variance function. So try it out. The max and min function works in a similar way as the sum function, but there is an important difference. So, if we create matrix A and then run this line of code, this will not return a column vector containing the maximum of each row as it did for the sum function. What this line of code does is that it compares matrix A with the number 2 element-wise, and then it returns the biggest element and forms a matrix of all the comparisons. So I run this line of code to illustrate, and we see that when comparing 1 and 2, 2 is bigger and 2 is exactly what we got here. Comparing 5 and 2, 5 is bigger and 5 is exactly what we got here, and so on for all the elements. If you would like to compare two matrices, that's easy to do. So first I create matrix B consisting of only 6s, and then I can type max A, B. What this line of code does is that it will compare matrix A and B element-wise and then return the biggest element for each comparison. So I run this line of code and we get the following answer. You can verify for yourself that this is the expected answer. Finally, if you really would like to produce a column vector containing the maximum of each row, then we run the following line of code. Notice that in the second argument we have an empty square bracket. The empty square bracket means that we leave that argument undefined. So in a sense, we don't do any comparison with matrix A with something else. So running this line of code, we see that we got a column vector containing the maximum of each row. If I display matrix A, then we see that the maximum of the first row is 7, and 7 is exactly what we got here. And the maximum of the second row is 3, and 3 is exactly what we got here. And the same goes for the third row. If we would like a row vector containing the maximum of each column, then we can simply change the dimension argument to 1. And running this line of code now, we see that we got a row vector containing the maximum of each column. Finally, the min function works in exactly the same way as the max function, so you can try that out yourself. Doing matrix calculations in MATLAB is straightforward. So let us begin with creating these three matrices. And notice that I have put a semicolon at the end of each matrix in order to suppress output. But we see here in the workspace that I have created the variables. So if I begin by typing B in the command window, I will display matrix B. If I type B prime, then I will get the transpose because prime is the transpose operator. So we see that the first column is now the first row and the second column is now the second row. I can do some simple calculations such as A minus A, then I will get a 0 matrix. If I do A minus B, I will get the error because the dimensions don't agree. So in order to solve this, I can for instance type A minus B prime and recall that prime is a transpose operator, and now I get this answer. I can also do matrix multiplication, for instance A multiplied by B, then we get the following. And recall that if I write out matrix A and matrix B, then matrix multiplication, to get the first entry, you take the first row of the first matrix and the first column of the second matrix. So 5 times 2 is 10, 2 times 3 is 6, summing up that we have 16, and 3 times 1 is 3, so summing up 16 and 3 we get 19, which is exactly this element here. So matrix multiplication works just as usual. C is a square matrix, so we can raise C to something, for instance C to the power of 3, then we get this result, and this is the same thing as C multiplied by C multiplied by C, and then we get the same thing. So doing matrix computations is straightforward in MATLAB, so try it yourself. Operators such as multiplication, division, and powers can be defined element-wise as well by writing a dot before the operator. For instance, creating these two matrices, A and B, then we see that this is matrix A and this is matrix B. If we type A dot multiplication sign B, then the multiplication will be performed element-wise. For instance, 5 multiplied by 1 is 5, 2 multiplied by 2 is 4, and so on. If I type CLC to clear the command window and display matrix A and matrix B again, we can also do division element-wise, for instance A dot slash B. This will do the division element-wise, for instance 5 divided by 1 is 5, 2 divided by 2 is 1, 3 divided by 1 is 3, and so on. So I type CLC to clear the command window. And finally, we can also do powers element-wise. So I display matrix A and type A dot raised to 2. Then we see that 5 raised to 2 is 25, 2 raised to 2 is 4, and so on. And as you might guess, addition and subtraction is already defined element-wise, so there's nothing new with those operators. The backslash operator, also called ML_divide, is used in the following way. If we have a system of equations of the form a multiplied by x is equal to b, then we can solve that system by writing x is equal to a backslash b. In order to understand this, let's look at an example. If we have the following equation system, x plus y is equal to 4 and 2x plus y is equal to 3, then we can easily solve this with Gaussian elimination, for instance. Taking the first row and subtracting that from the second one, we can see that x is equal to -1 and y is equal to 5. To verify that this indeed is the solution, we can plug x and y into the equations. So -1 plus 5 is 4, and 2 times -1 plus 5 is 3. So the solution is indeed x is equal to -1 and y is equal to 5. So to solve this system in MATLAB, we first create the coefficient matrix A. The first row is 1 and 1, representing the coefficients 1 and 1 in this first equation. And the second row of matrix A is equal to 2 and 1, representing the coefficient 2 and 1 in the second equation. Then we create a column vector B, which is the right-hand side of this equation system, 4 and 3. And then to solve the system, we type x is equal to a backslash b. So running this code, we see that the solution is -1 and 5, just as we verified above here. A word of warning. It is important to know what you do when you type in your MATLAB code. Typing in code is easy, but to understand what you're doing requires skill, in this case in linear algebra. So for example, if we have a matrix with m rows and n columns, where the number of rows is not equal to the number of columns, then we will get the least squares solution. So that's important to know. If you want to read more about the backslash operator, write doc backslash or doc ML_divide for the documentation. A closely related operator is the slash operator. Write doc slash or doc MR_divide to read more about the slash operator. So have a look at that. In linear algebra, two important concepts is determinant and rank. So if I create this matrix A, and if I would like to calculate the determinant of A, we know that the determinant of a 2 by 2 matrix is 1 multiplied by 3 minus 2 multiplied by 3. This is equal to -3, and if we write det of A, we get the answer -3, just as expected. We also see that the first column is 1 and 3, and the second column is 2 and 3. None of these columns is a linear combination of the other ones, so this matrix has rank 2. To double check this, we type rank A, and we get, just as expected, 2. For reference, if you want a complete list of matrix functions, you can type doc matfun, and here we get a list of matrix functions which can be worthwhile to explore. Relational operators perform element-by-element comparisons between arrays. In MATLAB, we have the following relational operators. Notice that the relational operator for equal to is two equal signs, and the relational operator for not equal to is a tilde and an equal sign. In general, a logical 1 means that a statement is true, and a logical 0 means that a statement is false. For instance, typing 2 is greater than 3, This is false, so we expect to get a logical 0, which is exactly what we got. Typing 10 is greater than 3 is true, so we expect to get a logical 1, which is exactly what we got. Continuing and creating two matrices, we might be interested to check which elements of matrix B are greater than or equal to 2. Then we simply type B greater than or equal to 2. If we want to check which elements of matrix A are greater than the elements of matrix B, then we simply type A greater than B, and then we see which elements of matrix A are greater than the corresponding elements of matrix B. If we want to see if sum of the elements of matrix A equals sum of the elements of matrix B, then we type A equal B, and we see that none of the two matrices have the same elements in the same position. Finally, there is a function that is called isEqual, and what that function does is that it compares the complete matrix A with the complete matrix B. So it doesn't do the comparison element-wise. So if we type A, B, we will get a logical 0 because the two matrices are not equal. But if we type isEqual A, we will get one logical 1 because matrix A is indeed equal to matrix A. The function Maxk is a function that returns the k largest elements from each column in a matrix. So if we create this matrix A and run the code here, then we will get the two largest elements from each column in matrix A. So to verify, in the first column, the two largest elements is 11 and 5, which is exactly what we got here. In the second column, the two largest elements is 110 and 13, which is exactly what we got here. However, the function Maxk is a function that allows for multiple outputs. And when you have a function with multiple outputs, the way to handle that is that you insert square brackets, and then you type the name of the first output variable, you put a comma, and then you type the name of the second output variable. So if I run this code here, I will first display matrix A, and then I will run this function which has two output variables. So I run the code, and here we have matrix A, and here we have the maximum values of each column, and here is the index of the maximum values. So in the first column, the maximum values are 11 and 5, which is exactly what we got here. And we also see that the index of the maximum value is 5 and 4, which is exactly what we got here. In the second column, the two largest values are 110 and 13, which is exactly what we got here. And the index of the two largest value are 1, 2, 3. So 3 is exactly what we got here. And then we have 1, 2, 3, 4, 5. So 5 is exactly what we got here. And so on. So in general, when you have a function that allows for multiple output values, you insert a square bracket and type the name of the first output variable, then you put a comma and type the name of the second output variable, and so on. Also note that the name of the output variable, you can choose that yourself. For instance, I can call max for m and index for I. If I rerun this code, we get exactly the same answer, but now the maximum is denoted by m and the index is denoted by I. So try this out yourself. In mathematics, we often have relationships of the form such as y is equal to x squared. If you want to have the same thing in MATLAB, then you simply type in this line of code and run it. Once you have run this line of code, we now have a function called y, and I can for instance type y of 2, and then I expect to get the answer 4 because 2 to the power of 2 is 4. If I type y of 9, I expect to get the answer 81 because 9 to the power of 2 is 81. And running this line of code, 81 is exactly what I got. This can be generalized to multiple arguments. So if I in this case call my function square2 and then write an equal sign at with the arguments x and y, and the rule is x squared plus y squared. So if I run this line of code, I can now, for instance, type square 2, 3, 2. 3 to the power of 2 is 9, and 2 to the power of 2 is 4, and 9 plus 4 is 13. So I expect to get the answer 13, which is exactly what I got. So these kind of functions can be useful if you need them. Saving variables is an important skill which we now will go through. If I begin with creating these variables, then we see that they show up here in the workspace window. If I run the following line of code, save important data, A, C, then I will save the variables A and C in a file called important data. The file important data will be saved in the current folder, and in my case the current folder is called MATLAB course. So I run this line of code, and we see that I got a new file in my current folder which is called importantdata.mat. The .mat extension indicates that this is a mat file. If I would like to save all my variables, then I can simply type save all data, and then I will create a new file, all data, that contains all the workspace variables, and the file all data will again be placed in current folder. So I run this line of code, and we see that I got a new file called all data. If you want to save some variables manually, you can do that as well. For instance, if I want to save variable A, then I can right click on it and press save as. Then I can choose what I want the file name to be and what the format of the file is, and the format should be a mat file. So I press save, and we see that I got a new file called a.mat. And again, .mat indicates that this is a mat file. So in this video we saved variables, and in the next video we are going to load variables. In the previous video we saved variables, and now it's time to load variables. So we see that in the current folder I have some files that is called a.mat, alldata.mat, and importantdata.mat. If I type in the following line of code and run it, then I will load variables b and d in the file called alldata.mat. So I run this line of code, and we see that in the workspace I now have the variables b and d. If I type clear in the command window to clear the workspace, if I want to load all the variables in a file, then I simply type load and the file name. So I run this line of code, and we see that I got all the variables contained in the file. Again, I type clear in the command window to clear the workspace. I can also load the variables manually if I wish. For instance, right-clicking on this and pressing load. Now I have loaded the variable a. In the folder MATLAB course, I have a subfolder called data. In this subfolder, I have a file called cement.dat, which I would like to load into MATLAB. The .dat extension indicates that this is a DAT file. So if I go to MATLAB and run the following line of code, load cement.dat, I get an error message. And the error message is telling that the file I'm trying to load is not found in the current folder or on the MATLAB path. This is easy to fix. I go to current folder and right-click on the subfolder data. Then I choose add to path and select selected folders. Once I have done this, we can notice that the subfolder data is no longer grayed out, which is indicating that the subfolder data is now on the MATLAB path. So if I run the same line of code now, we see that I have loaded the cement data file. Also notice that the file we loaded is a .dat file, and it is equally easy to load a .dat file as it is to load a mat file, which we did in the previous video. And I would also like to tell that if you want to do the same thing but writing code instead, then there is a function that is called add path. And the address I'm using as an argument is easy to obtain. You go to the folder and then you right-click and select copy address. And once you've done this, you can paste it in and you see that this address is exactly the one I've used here. So finally, I recommend you to type doc add path and read about that function. In a file called steps, a person have written down how many steps they did on each day for 10 days in a row. The data is saved as an Excel file, and we would like to load the data into MATLAB. This is straightforward to do, so you go to MATLAB, go to the Home tab and press Import Data. Then we go to the subfolder Data, where our file steps is saved. We double-click on steps and we come to the Import window. Now we can choose what output type we want. For instance, you can choose a matrix or column vectors. I choose column vectors. And we also see that the variable names row is the first one. Here, day and number of steps. Then we simply press Import and we get the message that the variables were imported. Minimizing this window, we see that in the workspace window we have imported the variables. And now we can, for instance, calculate the mean number of steps. And if I type mean and then type number, now I don't need to type the whole name. I can type the first letters and then press tab. And then I get suggestions and I press tab again and I have saved some time with this keyboard shortcut. I press enter and we see that approximately the person did almost 18,000 steps a day. And finally, I would also like to say that if you want to load CSV files, then you do that in the same way as you're loading Excel files. Accessing elements in a vector or matrix based on their index is called indexing. So if I create this vector x here, and let's say I want to access the third element of the vector x, then you simply type x parentheses 3, and running this line of code we see that we got exactly the third element. If you would like to extract the first, third and fourth element of the vector x, then you type x parentheses square bracket 1, 3 and 4. Running this line of code, we got exactly the first, third and fourth element of the vector x. If you would like to extract the last element of vector x, then you don't have to count backwards. You can simply type x parentheses end. And then we see that we got an 8, which indeed is the last element. If we would like to extract the first 4 and then the 9th to the last element of the vector, then you can type x parenthesis square bracket 1 colon 4 and then 9 colon end. And running this line of code, we got the first 4 elements and then the 9th to the last element. If you want the last 3 elements of the vector x, then again you don't have to count backwards. You can simply type x parenthesis end minus 2 colon end. And then we see that we got the last 3 elements, which is 15, 13, and 8. Finally, there is something that is called logical indexing. Let's say that you want to extract all the elements in the vector x which are greater than or equal to 10. What you do then is that you type x parenthesis and then x greater than or equal to 10, and running this line of code, we extracted all the elements in the vector x that are greater than or equal to 10. In this video, we're going to index into a matrix. So let's begin by creating matrix A. If we, for instance, type A parenthesis 2, 3, then we will get the element in the second row and third column. So running this line of code, we expect to get the number 4, which is exactly what we got. Indexing in this way is called positional indexing. If we would like to extract the first row of matrix A, then we can simply type A parenthesis 1, colon. Running this line of code, we see that we have extracted the first row of matrix A. This notation here is shorthand notation for the following: A parenthesis 1, 1, colon end. Running this line of code, we see that we got exactly the same thing, but since this notation is shorter, this notation is the one that you will see most often in practice. If we, for instance, want to extract the third column of matrix A, then we type A parenthesis colon, 3. Running this line of code, we see that we got the third column of matrix A. Now let's say that we would like to extract 2 elements from matrix A. The first element being the intersection of row 1 and column 3, and the second element being the intersection of row 1 and column 4. Our guess is that to extract these 2 elements, we should type A parenthesis square bracket 1, 3, comma, square bracket 1, 4. However, this is wrong and will not extract the 2 elements that we want. It will extract 4 elements. And try to figure out what we're doing when writing this line of code. If we want to extract specific elements, then we must use linear indexing. And when using linear indexing, the index runs down the columns. So for example, displaying matrix A again, when using linear indexing, this is the first index, this is the second, this is the third, this is the fourth, this is the fifth, and so on. So when using linear indexing, the index runs down the columns. So for example, typing A parenthesis 2 will extract a 8. Typing A parenthesis 5 will extract the 5th element. 1, 2, 3, 4, 5. So we expect to get the number 3. Running this line of code, number 3 is exactly what we got. Typing A parenthesis end, we expect to get the last element, which is 1, and running this line of code, we see that 1 is exactly the number that we got. If we, for instance, would like to extract the second, fifth, and last element, then we simply type A parenthesis square bracket 2, 5, and end. Running this line of code, we have now extracted 3 elements. Finally, there is something that's called logical indexing, and let's say that we would like to extract all the elements in matrix A that are greater than 10. then we type in the following code: a parenthesis a greater than 10, and running this line of code, we will extract all the elements in matrix A that are greater than 10. And in this case, this is the elements 13 and 11. Here we have a matrix that we call A, and it is a 4 by 4 matrix since it has 4 rows and 4 columns. In total, it has 16 elements. If we would like to create matrix A as a vector instead, then we can use the reshape function. So typing reshape A, and then we specify the dimensions. For instance, 16, 1. This will make A into a column vector, which we see here. We can also use a special command, which is the following: A parenthesis colon parenthesis. This will also make A to a column vector where we stack the columns of matrix A on top of each other. In MATLAB, it's easy to concatenate matrices in order to create a larger matrix. So let's create these 3 matrices first. And if we now would like to concatenate these 3 matrices on top of each other, then we can do that easily. Let's call the new matrix D, and then we type equal sign, square bracket, A, semicolon B, semicolon C. Running this line of code will now stack the matrices A, B, and C on top of each other. So running the line of code, we see that we have stacked the 3 matrices on top of each other. If we would like to remove the second row of matrix D, then we can easily do that by typing D parenthesis 2, semicolon, and then write equal sign empty square brackets. Running this line of code, we will now remove the second row of matrix D. If we want to remove the first and third element of matrix D, then we can use linear indexing. So we type D parenthesis square bracket 1 and 3 square bracket parenthesis equal sign a empty square bracket. This will delete the first and third element and change the matrix into a row vector. So running this line of code, we see that we have removed the first and third element, and the matrix is now transformed to a row vector. In this example, I have created a matrix A, and I would like to replace some elements in that matrix. So let's say that I want to change the element in the first row and third column to 100. So if I use positional indexing and run this line of code, we see that the 1 was replaced by 100. If I, for instance, want to change the third and the fifth element of the matrix A by 88, then I can use linear indexing and run this line of code. And indeed, we see that the third and fifth element was replaced by 88. If we would like to replace all the number 2's in matrix A by a 0, then we can use logical indexing. So if I run this line of code, then we see that the first and the last element was replaced by a 0. All the changes that we did here, we can sort of do manually. You simply double-click on the variable A in the workspace, and then we can, for instance, change the number 8 to 111. We can also insert rows or columns, and we can also delete rows and columns. Let's delete the third row. If I now close this window down and display matrix A again, then we see that we did the change to 111 here, and we also deleted the third row. If you create a vector y and then type plot y, for now you can ignore this part of the code, that's just line specification, and we will come to that later. So I create a vector y and then I type plot y. If I run this part of the code, we will produce a piecewise linear graph where we plot the elements of y versus the index of the elements of y. So pressing F9 to run this part of the code, we see that we have plotted the elements of y, that is 2, 3, -2, and 3, which is exactly the elements of y, against the index of the elements, that is 1, 2, 3, and 4. We also see that the graph is piecewise linear between the elements of y. If we now create a vector x which is linearly spaced between -4 and 4 with 100 points between, and then we type plot x to the power of 2 element-wise, and that the operation is element-wise is indicated by this dot here. So I run this part of the code, then we see that we get a misleading graph, and the source of confusion is that the x-axis contains the index of the elements, and this might fool you to think that, for instance, 50 to the power of 2 is 0 and 100 to the power of 2 is 16. This is obviously wrong. The correct way of doing this would be to type plot x and then x to the power of 2 element-wise. This will plot the elements of x to the power of 2 against the elements of x. And pressing F9 to run this part of the code, we see that we get a graph which no longer is misleading. For example, 0 to the power of 2 is 0 and 4 to the power of 2 is 16. So this way of plotting it is not misleading anymore. As a final example, let's create a vector x1 which is linearly spaced between -4 and 4 with only 3 points in between. And then we create a vector y1 which is the power of 2 of the elements of x1 element-wise. And then finally we plot y1 against the elements of x1. So if I run this part of the code, we will get a misleading graph again. And as we see, the edges are sort of very sharp, and the reason for this is that we only have 3 points in the lin space. If we increase the number of points, let's say to 8, then we will get a much smoother graph. So rerunning the code, we see that the graph now is much smoother. And if you increase the number of points between -4 and 4 even more, let's say to 80 points, we will get a very good graph, as we see here. So it's important that you have enough points between the start value and end value when you use linspace. Plotting in MATLAB is very important, so try all of these examples yourself. Here we have a plot of x to the power of 2, and very naturally one would, for instance, like to have a title, a x label, a y label, and perhaps change the limits of the x-axis. All of this is very easy to do in MATLAB, and if you, for instance, want a title, then you type title, parenthesis, apostrophe, and then the title text. The same goes for X label and Y label. If you want to change the limits of the x-axis, then you type xlim, parenthesis, square bracket, and then type the lower limit and then the upper limit of the x-axis. Ylim works in exactly the same way as xlim, and as you might guess, ylim lets you change the limits of the y-axis. So rerunning this code, we press Ctrl Enter, and we see that we now got a new plot where we also have a title text, a X label, a Y label, and we have also changed the limits of the X-axis. When doing plots in MATLAB, it's possible to change the line specification. So for example, if we run this line of code, we will create a plot where the line style is dotted, the marker are plus signs, and the color is blue. So I run this code, and we see that the line style is dotted, the markers are plus signs, and the color is blue, just as expected. If we want to see a complete list of the possible line styles, markers, and colors, then you can type docplot to see the documentation about the plot function. And if you then go down, then you see that there are different choices for line style, marker, and color. Also notice that the symbols can appear in any order and you do not need to specify all three characteristics. This is good to know. If you would like to do this sort of manually, that is also possible. So if we now only type plot xy and run the code, then we got a standard plot. And if you want to change the line style specification, then you can go to Tools, Edit Plot, and once you have pressed Edit Plot, you simply right-click on the line, and then you can, for instance, choose the color. Let's take red. And then if we right-click on the line again, then we can, for instance, choose the marker. Let's take a pentagram. And there we have it. So try this yourself. Quite often, one wants to add multiple plots to one figure window in MATLAB. So we begin by creating the vector x. Then we create a function y1, which is equal to x squared. And then we create a function y2, which is equal to 2x squared. Then we plot y1 against x, and we type hold on. The hold on command tells MATLAB that we want to add a plot to the existing figure window. Then we plot y2 against x, and we type hold off. The hold off command tells MATLAB that no more plots should be added to the existing figure window. Finally, we add a legend so that we can distinguish between the functions. This is the first label, and this is the second label. So running this code, we see that we have done two plots in one figure window. With the legend, it's also easy to distinguish between the functions. And notice that when we changed the line specification for x squared, then the legend adjusted properly. So it's really easy to distinguish between the two functions. If we would like to add some grid, then that is also possible. Then you type grid on, and we see that now we have a grid. We can also choose to have a minor grid, and then we type grid minor, and now we have a minor grid. And of course, you could combine them both. So then you type grid minor and grid on. Now we have a larger and minor grid. Sometimes you want to display multiple plots by splitting the figure window into a grid. So here I have created 4 functions which I want to plot, and I will now press Ctrl Enter to run the code and then explain what has happened. So pressing Ctrl Enter, we got the following figure. We can see that I have created a grid consisting of 1 row and 4 columns. In the first subplot, I have plotted cosine of x, and I have a title cosine of x. In the second subplot, I have plotted sinus of x, and I have a title sine of x. And so on. We also see that I have an overall title which says plots of trigonometric functions. So looking at the code, we see that first I wrote subplot 141, This means that I am splitting the figure window into a 1x4 grid, meaning it has 1 row and 4 columns. And then this is the first subplot. Then I do the plot, in this case y1 against x, and y1 is cosine of x. And then we also have a title, which is cosine of x, just as we see here. I continue in this fashion, and then at the end we see that I have typed SK title, and this produces a main title for all the subplots. So this was one way of doing it. Another way would be to create a 2x2 grid. So if we go down, now I have typed subplot 2, 2, 1, subplot 2, 2, 2, and so on. Running this code, we see that now I have created a 2x2 grid, and perhaps this is giving a better view. So try this yourself. If we have multiple plots in a section, it will only plot the last one. For example, here I have created 3 functions and written plot 3 times. Running the code in this section will, however, only produce the last plot, so the plot will be a plot of the exponential function. Pressing Ctrl Enter to run the code, we see that we only got 1 plot. If you would like to plot all 3 functions in separate figure windows, then you can use the command figure. So if I run this line of code, I press F9, then I have created an empty figure window. If I now run plot x, y1, then I will plot y1 against x on the previously empty figure window. If I type CLF, then I will clear the figure window again. So I run CLF, and we see that now the figure window has been cleared. So running the code in this section will produce 3 figure windows and do the plots on each one of them. So I press Ctrl Enter to run the code, and we see that we got 3 plots plotting each of the 3 functions. If you run the code in this section multiple times, you will get multiple figure windows, and if you want to close the current figure, which in this case is figure 9, then you can simply type close. Now we see that figure 9 have been closed. And we can also close them manually like this, but if you have done many plots, this quickly becomes tedious, and then the command close all saves the day. So by typing close all and running the code, now I have closed all figure windows. Scatterplots, sometimes also called bubble plots, are used when you try to determine whether 2 variables are related. So here I have created 2 vectors, x and y, and if I then type scatter x, y, I will create a scatter plot where the first bubble will be located at the coordinate 1, 3. The second bubble will be located at the coordinate 2, 1, and so on. So if I run this code, we see that the first bubble, just as expected, is located at the coordinate 1, 3. The second bubble is located at the coordinate 2, 1, and so on. In the next example, we have done some measurements of length and weight of some individuals. If we run this code, we get a new scatter plot, and just as expected, there seems to be a positive relationship between weight and length. If you think about this, this is very reasonable. In the previous video, we made the following scatter plot, and we said that there seems to be a positive relationship. If we continue to look at this plot, we also see that there seems to be 2 extreme observations. The first one being this one, and the second one being this one. For example, this individual is 210 centimeters long and weighs little less than 90 kilos. So naturally, we would like to highlight then these two extreme observations. This we can easily do by going to Tools and then select Brush. If we now simply click on this observation, we see that it is highlighted. Notice that if I also click on this observation, then this highlighting will disappear. So I click on this observation and we saw how this highlighting disappeared. To solve this, simply hold the Shift key. So I hold the Shift key and then I can select this observation as well. If you would like to select a range of observations, then you can simply draw a rectangle like this. But in my case, I will only select these two outlier values. Also notice that if you go to Tools and Brushing, you can for instance choose which color you want to do the highlighting with. But I am happy with the color red. Naturally, we would for instance now want to create a variable containing these two outlier values. This we can easily do by again going to Tools, Brushing, and then Export Brushed. I will call the variable name for outliers. Pressing OK, we now see that in the workspace we have a new variable called outliers that contains the interesting observations. Once you're happy with your plot, it is easy to save it. You simply go to File and press Save As. Then you can choose the file name, and I will call it Plot, and you can choose the file format. Some choices are MATLAB figure, JPEG image, and PDF. If you're going to use your plot in a Microsoft Word document or LaTeX document, then PDF is a suitable choice. The advantage with saving your plot as a MATLAB figure is that you can edit it afterwards. So if I save my plot in the desktop, then we can reopen it and edit it. So I open up the plot and I can for instance press Tools, Edit Plot, and then right click on the bubbles and for instance change the color. I can choose green. So, saving a plot in MATLAB is straightforward. In this example, we have created three normal distributions. The first one is standard normal with mean 0 and standard deviation 1. The second one has mean 0 and standard deviation 3. And the last one has mean 4 and standard deviation 1. If we run this code, then we will plot the distributions, and if you need a recap about plotting, then go back to the chapter about plotting. So I press Ctrl Enter to run this code, and we get the following plot. We see that the blue distribution is standard normal, and the red distribution is a normal distribution with mean 0 and standard deviation 3. Notice that when we increase the standard deviation, the tails get fatter. Fatter tails means that extreme events are more likely to occur. In the second subplot, we see that if we increase the mean of the normal distribution, then the distribution is shifted to the right. So in this example, we use the probability density function to plot a distribution. We can also use the probability density function to calculate probabilities for discrete random variables. For example, if we toss a fair coin 10 times, what is the probability of getting 3 heads? This we can easily calculate with the following line of code. N choose k is the binomial coefficient, and in this case, it returns the number of combinations when choosing 3 items out of 10. And then we multiply by the probabilities. So if I run this line of code, we get the answer 0.1172. If we would like to do this in a quicker way, then we can simply use the binu pdf function. So I type binu pdf, and then the first argument x should be 3 because we want the probability of getting 3 heads. N is 10 because we have 10 trials, and p is 0.5 because the coin is fair. Running this code, we see that again we get 0.1172. But probably this way is much quicker, so we prefer to use this instead. Finally, if you want a complete list of all the probability density functions, then we can first clear the command window by typing clc, and then we can type help stats. So I type help stats and press enter. Then if we go up, we see that we can get many different probability density functions. For instance, if we want a beta density, then use the function beta pdf. If you want a binomial density, then use the function binu pdf, and so on. And as you can notice, the generical structure of the pdf function is distribution name and then pdf. So check this out yourself. The cumulative distribution function, CDF, is defined as the probability that the random variable x is less than or equal to little x. This is often denoted by a capital F, where the random variable x is put as a subscript and then evaluated at little x. So this is just notation for this. Let's look at an example. We have a random variable x which is normally distributed with mean 2 and standard deviation 4. We want to calculate the probability that the random variable x is less than or equal to 6.4. To solve this, we begin with standardizing. We remove the mean from both sides, and then we divide with the standard deviation on both sides. It's easy to check that the mean of the left-hand side is 0 and that the standard deviation is 1. It is also a well-known fact that a linear transformation of a normal random variable is still normal. So this simply is the distribution function of the standard normal distribution evaluated at 1.1. We got 1.1 because 6.4 minus 2 is 4.4, and divide that by 4 is exactly 1.1. Analytically, we have that the distribution function of the standard normal distribution evaluated at 1.1 is equal to the integral from minus infinity to 1.1 of the following function. This function is the density function of the standard normal distribution. To solve this integral, we use MATLAB, table, or a calculator, and this we will do in the next video. In the previous video, we looked at an example. In this video, we're going to do the computations. First, we're going to do the computation in MATLAB, then we're going to use a table, and then I will give a remark if you do the computation with a Casio calculator. So let's begin by doing the computation in MATLAB. We want to compute the probability that the random variable x is less than or equal to 1.1, and x is standard normal. To do this, we use the cumulative distribution function of the normal distribution, and in MATLAB that function is called normCDF. The first argument is 1.1, the second argument mu, which is the mean, is 0, and the third argument sigma, which is the standard deviation, is 1. So running this line of code, we get the answer 0.8643. Notice that by default, mu is 0 and sigma is 1. So if you leave those arguments out, you will still get the same answer. So we type norm CDF 1.1, and running this line of code, we see that we get exactly the same answer. In MATLAB, you don't have to standardize, so you can compute this probability directly. We simply type norm CDF, the first argument is 6.4, the mean is 2, and the standard deviation is 4. So running this line of code, we see that again we get the same answer. If you want to do the computation with a table, you can go to the following link. I have already prepared that, so I go to the link and we see that we have a table for the standard normal distribution. So we find the corresponding z-value, and in our case the z-value is 1.1, and we see that the value we search for is 0.86433. If you would like to display more digits in MATLAB, that is easy. You simply type format long, and if we redo this computation, we see that now we have displayed more digits. If you want to display less digits again, then you simply type format short. And redoing the computation, we see that now less digits are displayed. I also want to give a remark if you do the computation with a Casio calculator. Then you can go to the following link, which I also have prepared. So I go to that link. And then we see that if you're doing the computation in this calculator, then the argument for sigma comes before the argument for mu. In MATLAB, the argument for mu comes before the argument for sigma. So you have to be aware of that. Now let's look at another example. We want to compute the probability that we get 0, 1, 2, or 3 heads when tossing a fair coin 10 times. To compute this probability, we can use the binomial distribution and then first compute the probability for 0 successes, then compute the probability for 1 success, and so on. And then we sum up all those probabilities and we get the answer. So pressing Ctrl Enter to run the code, we see that the probability is 0.1719. If we want to do this in a faster way, we can use the cumulative distribution function for the binomial distribution. In MATLAB it is called binu CDF. So I type binu CDF. The first argument is 3. Then n is 10 because we have 10 trials, and p is 0.5 because the coin is fair. So running this line of code, we see that again we get 0.1719. Finally, if you want to see a complete list of all the cumulative distribution functions for different distributions, then we can first clear the command window. We type clc. And if you now type help stats and scroll up, then we see a list of the cumulative distribution functions for different distributions. Also notice the generic structure. First the distribution name and then CDF. The cumulative distribution function takes a value as input and returns a probability. For the standard normal distribution, the probability that we get a value less than or equal to minus 0.5244 is equal to 0.3. The lower quantile function, which is the inverse CDF, takes a probability as input and returns a value. For the standard normal distribution, the lower quantile function, evaluated at 0.3, is equal to minus 0.5244. So by looking at these two examples, we see that the CDF and lower quantile does the opposite thing. So we have made it somewhat plausible that the lower quantile function is the inverse to the CDF. The lower quantile is sometimes called quantile, inverse CDF, or in Swedish, percentile. The alpha lower quantile is for a continuous distribution defined as the x alpha such that the following equality holds. The probability that the random variable x is less than or equal to x alpha is equal to alpha. Visually, we can view this as the area to the left. The alpha upper quantile is for a continuous distribution defined as the x alpha such that the following equality holds. The probability that the random variable x is greater than x alpha is equal to alpha. Visually, we can view this as area to the right. The upper quantile is sometimes called quantile, or in Swedish, Quantile. So notice the source of confusion. In English, quantile often refers to the lower quantile, but can be used for upper quantile as well. So when reading the literature, make sure that you know what the author means by quantile. As you know, the area under a probability density function is equal to 1. So if there is alpha probability to the right, then necessarily it has to be 1 minus alpha probability to the left. This knowledge we will use in the next video. In this example, we want to find the upper 2.5% quantile of the standard normal distribution. To do this, we simply type norm_inv, and if there is 0.025 probability to the right, then there should be 1 minus 0.025 probability to the left. Mu, which is the mean, is equal to 0 in this case, and sigma, which is the standard deviation, is equal to 1 in this case. So running this line of code, we get the answer 1.96. And as I said, if there is 0.025 probability to the right, then there should be 0.975 probability to the left. So to double check this, we can type norm CDF, and the first argument is 1.96, which was our answer before. And then mu is 0 and sigma is 1. So running this line of code, we expect to get the answer 0.975. And pressing F9 to run this code, 0.975 is exactly what we got. To see a complete list of the inverse cumulative distribution functions for different distributions, then you can type help stats. And by now, you might guess that the generical structure is distribution name and then inv, which stands for inverse. For other discrete distributions, such as the Poisson distribution, read the documentation of what the inverse function does. The following quote illustrates what pseudo-random numbers are. If you're not that interested, you can simply skip it, because for our practical purposes, we view the generated numbers as completely random. So, if we run the following line of code, we will get a uniformly distributed random number in the interval 0 to 1. So I press F9 to run the line of code, and we got the following value. If I press F9 again, then we get another one. If we run the command rand3, we will get a 3x3 matrix consisting of uniformly distributed random numbers in the interval 0 to 1. So I run this line of code, and here we see that we got a 3 by 3 matrix. If we run this command norm rand with the parameters 10, 2, 3 and 5, then we will get a 3 by 5 matrix consisting of random numbers from the normal distribution with mean 10 and standard deviation 2. So I run this line of code and we got the following 3 by 5 matrix. If we run the command rand n with the parameters 2, 5, then we will get a 2 by 5 matrix consisting of random numbers from the standard normal distribution, meaning it has mean 0 and standard deviation 1. So I run this line of the code and we get the following matrix. If we want random numbers from the binomial distribution, then we can use the function binu rand. If we use the parameters 10, 0.7 and 2, 3, then we will get a 2 by 3 matrix consisting of random numbers from the binomial distribution with parameter n equal to 10 and p equal to 0.7. So I run this line of the code and we got the following values. And as you see, it is a 2 by 3 matrix. Finally, if we clear the command window by typing clc, then we can type help stats to check the different random number generators. So I type help stats, and scrolling up, then we see that here we have the list of random number generators. And as you might guess, the generical structure of this function is distribution name and then rand. For example, beta rand. In this example, I have simulated 400 observations from the exponential distribution with mean 3. Assume now that we don't know from which distribution the observations come from. Our mission is to use graphical techniques to find a suitable distribution for the data. So if we begin by running the code histx, we will produce a histogram of the data, and looking at this plot, an exponential distribution seems to be a reasonable choice. If we run the function histfit of x, then once again we will produce a histogram of the data, and by default we get a normal distribution fit, as we see by this red line. Looking at the plot, we see that all the observations are positive, whereas the normal distribution allows for negative values. This indicates that the normal distribution is a poor fit. The function histfit allows for more arguments, so we type histfit. The data is still x. The number of bins has to be a positive integer, and as a rule of thumb, the number of bins should be approximately equal to the square root of number of observations. In our case, we have 400 observations, and the square root of 400 is 20, so I choose 20 bins, and then the distribution I choose exponential. Running this line of code, we see that the exponential distribution seems to be a very good fit to the data. Another graphical technique matches the quantiles of the sample data to the quantiles of a given probability distribution. It is often called a probability plot or QQ plot. So with this code, my first subplot is a normal probability plot. My second subplot is also a normal probability plot, but with this line of code, I want to illustrate that there is a separate function for the normal probability plot. So this line of code does exactly the same thing as this line of code. And then finally, we produce an exponential probability plot. So running this code, we get the following plots. Large deviations from the line indicates a poor fit. So looking at these three plots, our choice would once again be the exponential distribution. Finally, if I go to the documentation pages that I have prepared, then we see that for the function Histfit, the following distributions are supported. And for the function probplot, the following distributions can be used. In the previous video, we decided to use the exponential distribution to model our data. Now it's time to get an estimate of the parameter, which is straightforward to obtain by using the function Fitdist. Our data is called x, which you can recall by the first line here. And our distribution name is exponential. So running this line of code, we get a point estimate of approximately 2.9 and a 95% confidence interval. Notice that the 95% confidence interval covers the true value of 3. And in this example, we know that the true value is 3 because we simulated the data ourselves. Finally, if we go to the documentation page for the function Fitdist, which I already have prepared, then here we see a list of distributions that we can use. The Pearson correlation coefficient, often just called the correlation coefficient, measures the direction and strength of the linear relationship between two random variables. The correlation coefficient always lies between -1 and 1, and the correlation coefficient of a random variable with itself is always 1. So, in this example, we're going to simulate 100 observations of two random variables coming from a multivariate normal distribution. And the reason why I chose a multivariate normal distribution is that I want to be able to control the dependence between the two random variables. But the focus of this video really is not the multivariate normal distribution, so just pretend that the data comes from some experiment and we shall now try to do some educated guesses about the random variables. This code will simulate the data, and then we're going to plot observations of the first random variable against the observations of the second random variable, and looking at this plot, we're going to try to conclude, is it a positive or negative relationship, and is it a strong or weak one? Having looked at the plot, we're then going to look at the correlation coefficient matrix and see whether the plot and the correlation coefficient matrix is consistent. So to run this code, I press Ctrl Enter, and then we see that the relationship between our observations seems to be positive and it is quite strong. And looking at the correlation coefficient matrix, we see that it is a positive number and it is quite close to 1. If I change my rho parameter to, for instance, 0.2 and run the code again, then we see that it seems to be a very weak positive relationship, and looking at the correlation coefficient matrix, we see that the number is positive, but it is quite close to 0, just as expected, because the relationship is positive, but it is not very strong. If we finally change the rho parameter once again to, let's say, -0.99, now we see that it seems to be a negative relationship and it is very, very strong. And looking at the correlation coefficient matrix, we see that the correlation coefficient is negative and very close to -1, which is consistent with this plot here. If you read the documentation about the correlation coefficient matrix function, then you will see that it is also possible to obtain confidence intervals. So do read the documentation.